All right, so your programming test number 3 will be this Wednesday, right? That'll be the last test before the exam. My maybe last minute advice, try to redo lab number 4. It's going to help for sure. And the practice test I gave to you also can help. If you really have time left, you can either choose to redo either one of them, or you can maybe go back to maybe the practice test for programming test 2. That might help as well, because that one kind of cover, the basic OOP. I think you just want to get yourself proficient about programming. That's really the emphasis for the programming test. Okay, but if you got any doubts about programming concept, I still got office hour today, 6 p.m. Okay, if you want to see me. And your lab number 5 has just been released yesterday. So that one there, you can either choose to submit before December 2nd. So that's the original kind of deadline on the semester calendar. I'll keep it the same. However, since I kind of released that late, it's not your fault. So I kind of gave a grace period. So you can take one more week if you want to, just to do a little bit more work on your end, from your end, and then you can submit by December 9th with no penalty. You still get your lab marks fully. And then I will post a solution right after this. So you can also take a look at the solution. Okay. And then just please know that there are 2 topics you are required to study to really complete this lab. So given that we already had some very thorough discussion about inheritance from programming and also from the theoretical point of view, it should now be very natural for you to learn about abstract classes and also interfaces. So these 2 are the very common constructs you also have to use whenever you want to program inheritance. So take some time studying for these 2. I gave you the slides, notes, lecture videos. You can choose the one that's going to work for you. You can just choose. Just learn the concept and then make sure you get ready about these 2 topics for the exam. So they will be covered as well, right? But I definitely got enough time to catch up with these 2 concepts. Okay. All right. Any questions? Yeah.
It's a bit unrelated, but I just want to check the final that we have in this case, the final exam. Do you know what date it is specifically?
I believe it's December 16th, right? Yeah, 9 a.m. Sorry, it's quite early, so please try to go to bed a little bit earlier the night before. Okay, I believe it's in the gym, not the Sobe this time, right? But guys, please double check. I just checked it yesterday. And then I'll maybe send out some survey polling just to see which day you might prefer to do a review session. We can meet again on campus. We choose a time that works for you, and then we can go over maybe some practice questions or even clarify your doubts. I'll host it myself. So we'll see each other again for sure. Okay. All right, any questions? Oh, I forgot, for your written test number 2, I'm going to meet with the TA very, very soon, and then I will ask them to hopefully finish the grading by Friday. So I'll just release the mark right afterwards, okay? Because there's one question there, if you remember, that require manual grading. So we'll just let the TA do that quickly, okay? I'll keep you posted. Friday should be good, okay? All right, good. I would say today, let's skip the recap, because the last thing we did on Wednesday was just about the last bit for inheritance. So please review about everything about inheritance has been fully covered. Look at the notes, look at the slides, and also start going over material for your exam. Okay, so I would say we'll start fresh about recursion. So this recursion here, I only plan to use 3 lectures, for talking about recursion. We'll definitely cover more in the follow-up course next semester in 2101. Well, if you take it with me. So that recursion that we're going to cover here, I don't assume any prior knowledge about recursion. So if you haven't learned about recursion before, it's absolutely okay, right? Just make sure you kind of try to follow through the intuition I try to teach you in the 3 classes. We're going to go over quite a bit of example as well, just to build the intuition. And remember, I kind of mentioned, let me just mention it again. All the study materials you have for the recursion, quite a bit actually, just on this section over here. So you got slides, you got past lab, you got examples, you even got some tutorial session, right? The whole section, you got everything there. So maybe start just familiarizing yourself about what's really available there. As we cover more and more stuff today and also Wednesday, I think you will be able to start tackling the exercise problem I gave to you. Also the coding bat site I gave to you, at least try the very first one. Of course, ideally, you can try all the problems. That'll be great. But if you really got limited time, try at least a few, just to get a feel, right? All right. So let's now talk about recursion. Let me go over some slides, and then we'll talk about some intuition. Okay, recursion. So we're going to learn about how to solve problems recursively. So we're really trying to learn about recursive thinking. Once you know how to really think recursively, you can apply that thinking to any programming language. Basically, any programming language you may have to work with will support recursion, right? Just a function or a method calls itself. We'll see exactly how that's going to work. And then we'll see example recursion problems. So we're going to just do, first of all, like a recursion on strings. So that'll be the like an easier one to really think about. So we'll talk about 3 examples there. And then we're going to move on to how you can call recursions on arrays. And we're going to revisit call by value again, just to see how useful call by value might be to save the time and also save the spaces at the runtime. We'll get there, okay? Most likely Wednesday. And then we'll try to see if we can talk about also one more advanced example, which is called the Tower of Hanoi. So that's really already on the slides. I'll see if I can get there. If I really cannot, I do have some nice recording there for you to also follow through. But the slide, you got to make sure you study for the Tower of Hanoi. It's definitely part of the exam. We'll see. If I can also give you some highlights and intuition, I'll definitely try to do that in the last class next Monday. All right, so beyond this lecture, well, usually I should really talk about this at last, but I wanted to say right away. So you got all the resources, especially for coding BET, okay? And then for those of you beyond this course, what might be the best way to pick up recursion? I would say we got very limited time, for each course to really teach you recursion, even throughout all your courses in the curriculum. So I would say for those of you who really want to master recursion, this will be my personal advice. You should really learn so-called a functional programming language. And that one there, you will use recursion basically for every construct that you have to program. That'll be my best advice. There's another advice I would usually give to students about learning recursion, but that'll be at the end of the 2101. At this level, you don't have to get there. Okay? So learning a new language is fun, but it's also a very good way for you to actually master recursion. Okay? That's not for this course, but maybe beyond this course. Okay? And Haskell over here, the language and listing is one of the mainstream languages people are using even in the industry. It's definitely relevant to your future career or if you stay in academia, either way. All right, recursion. The principle is very simple. Let's go over just a few bullet points and then we'll try to visualize it and then we'll do examples, okay? The recursion principle is going to be applicable to, doesn't matter how difficult the problem might be. It can be as easy as something like a factorial or Fibonacci number that we're going to talk about today, or it could be as advanced as maybe something you learned about how to do recursion on trees in 2101, right? So the same principle, okay? Okay, recursion is very useful in expressing solutions to problems that can be recursively defined. In order to really program recursively, first of all, you have to somehow understand the problem itself recursively. Okay? So that's really the first thing to mention. And whenever you want to give a solution, like a recursive solution, there are 2 things you have to worry about. Usually the first part here will be easier to really work with to start with. One will be the base cases. Thinking about if you're trying to solve some very, very small problems, almost like a trivial cases, but they should still be solved. Think about those ones first. Usually that will involve very simple computation to be done. Base cases, just base. And the second part here is about recursive cases. And this part here is going to be very up to your creativity, really. We can definitely go over certain pattern and certain example just for you to get some feel. But to really work out exactly how to come up with recursive cases in general, you have to build up some experience in programming. So that's why you have to expose yourself maybe to some functional programming language or try to work out different problems. Okay, that's really something I cannot really help you too much. You have to spend some extra efforts beyond this course. Okay. So recursive cases, basically, rather than solving some big problem right away, we try to reduce that into smaller problem and try to divide and conquer. That's what we call. All right. So these are the bullet points for the principle. Very simple, okay, and incredibly powerful at the same time. Let's try to visualize this very quickly, and then we'll start talking about some example. Okay. So the blue one is simply like a problem. Okay, the blue ones are simply the problem, and the green ones are the solution. And somehow we want to understand the problem recursively so that we can program some recursive solution accordingly. So both the problem and the solution are both recursive. Okay, how can we think of it? Base case will be right here. So this part here is the base case. Base case. So this is saying if I got a very small size problem, in that case, I can solve it right away. Let's say if the input array is simply of length 0 or length 1, very small input, and then I can solve it right away. Okay? If the input size of the array is somehow larger than just 1, in that case, I can consider that as too big to be solved right away. In that case, I can try to do a little bit massaging of the problem. Okay? So here will come the recursive case. Okay? Let's talk about conceptually what that really means. So this will be the recursive case. Okay, what does that mean? I'm given a problem. Apparently, it's strictly larger than something that's basic. I cannot solve it right away. The idea will be, first of all, I want to divide. The first step to do is called divide. I divide this particular big problem into strictly smaller pieces. You can divide to as many as you like. Okay, it's called a divide. Okay, so now I got something that's strictly smaller, something that's strictly smaller, and something that's strictly smaller. For the strictly smaller problem, here comes the magical part. But of course, in fact, it's no magic, but it might seem to be like a magic. For everything that we kind of have a smaller problem, you can see it's a smaller problem, number 1, smaller problem, number 2, and smaller problem, number 3. Now we assume for each of the strictly smaller problem, there is a solution. We assume. You can safely assume. Okay? So this part here, we assume the solution to smaller problem. In which case, we got solution for smaller problem number 1, the solution for smaller problem number 2, and solution to smaller problem number 3. Programmatically, whenever I say I assume there's a solution, that means I can make a method call on some strictly smaller input and assume it's going to return back to me the correct result. For this one, I'm going to write it down. This is the most difficult step to really get right, of course. And this one here in Java, for example, programming. You basically make recursive calls on smaller inputs and assume correct outputs return. So this may not make much sense just for now because we haven't seen any example. I'll try to revisit this concept. I'll try to re-emphasize it over and over. Okay, but this is a very important step to really grasp. Okay, you make some recursive call. Every recursive call is going to be on some strictly smaller input, and we assume it's going to return back to us the correct result. Okay, so once we got solution, solution, and solution, we cannot return all the 3 solutions separately. We have to return a single solution for the original problem. So what we do is we somehow try to combine them together. All right. So this is the part we are trying to do. So getting all the solution here, getting another solution here, we try to somehow concur. Well, in some way, you're trying to combine the solution. Of course, I'm going to put in quote. What does combine really mean? It really depends on the problem you're dealing with. For example, sometimes combine simply means I try to divide my input string into different parts. Once I got the solution for different part, I may just concatenate them together. Or maybe I divide my input array into different parts. Once I got a result from individual part of the array, I may just try to maybe also try to group them together in some way. Okay, but we'll see example. All right, so this one here just conceptually, right? So this pattern here is very powerful. We're gonna apply just the same pattern for every problem we're gonna solve recursively. Okay, we'll see. All right, so programmatically, so whenever beg your pardon, it should be back here. Whenever you're seeing some method call, right? I'm defining some method. If you see the method is calling itself, that means it's called a recursive call. The method calling itself. So this is called a recursive call to the same method, right? You can see M here and M here. And then conceptually, let's say M here is taking some value I. So this is the input that's given. But to make a recursive call, you have to make a strictly smaller input. if you don't make the input strictly smaller, you're going to run into infinite recursion, which we'll see. All right? So the j here must be a strictly smaller input. So in this case, for example, j, the new input should be strictly less than the original input I. But we'll see. You'll see many examples like this. Okay, let me recap very quickly. Whenever you want to solve a problem recursively, two phases. Phase number one, think about those problem instances that simply just trivial, very small. You can solve them right away without worrying about any recursive call. You can just solve them. Okay. Phase number two, you have to think about for any problem instances that might be beyond the size of being basic. So if you got a big problem here, first of all, divide them into smaller problem instances. Each one of them must be strictly smaller than the original problem instance, number one. All right? And then we assume for each problem instance over here, we have the corresponding solution. We can assume. Okay? And then from each one of them that we got the return value from the correct solution, we can combine them into the ultimate solution, which is here for the original problem. Okay? Divide and then conquer. All right. Any questions so far? Very abstract, I know, but it's good to just give you some very quick intuition before we see the example. All right. And then if you see on the slides, we just finished discussing slide number 4, and then slide number 5 is just a quick review about stack. And this part here I'm going to skip because we already talked about how to trace method call using a stack. We're going to do an example today as well. So remember when we talk about the exceptions lecture, we talk about how you can just go to different method call and how the method call may be suspended when there's something branching out, right? So that's the same thing. So we don't have to do it again. Okay, let's talk about our very first example. Okay, factorial. I'll leave this page over here clean. You can do whatever exercise you want to. Okay, factorial. Right, so for example, so here so this is a definition for factorial. I have some number n, okay, and we assume that, so this is an assumption here. The n here we assume it's not negative. Okay, could be 0, could be 1, could be 2, right? Whatever number you like, but just cannot be negative. Okay, let's look at this definition here. We're saying the following. Whenever I want to calculate n factorial, if n happen to be 1, by definition, beg your pardon. When n is actually 0, in that case, it's going to be 1. Okay, because n here, you can see larger than or equal to 0, right? When it's equal to 0, the smallest possible value for the input is, by definition, just 1. On the other hand, if I got any input that's strictly larger than 0, starting from 1, in that way, I'm going to get this particular definition. You basically just go from n and then n minus 1 all the way down to 1 and take the products of all of them together, right? The simple definition for factorial, right? And, well, just in case, 4 factorial will be 4 times 3 times 2 times 1, which will be 24, right? Just one example. I'm pretty sure you know that, right? So now, let's start by talking about this particular solution. According to our discussion earlier, this solution here is not recursive. This is not a recursive solution. All right? Since you're still not 100% familiar with the concept, so I can go directly to the answer. Okay? So here you can think about, we say that you can think about explanation mark over here is about we're taking the factorial of n of certain size. However, in the solution itself, we never try to use the explanation mark again on some strictly smaller input. If a solution has to be recursive, you have to somehow reuse the function itself, but it's not the case. All right? So, simply because the explanation mark is not used, or you can say reused, in the solution. Especially, you can see for this part over here, we didn't say anything about, for example, n minus 1 factorial. We didn't say that, right? We simply say it's going to be explicitly, we're going to multiply n, then n minus 1, all the way down to 1. Very explicit. So it's not recursive solution. It will work, but just not recursive solution. What we want to do is we want to somehow see what will be the corresponding recursive solution and compare. And then we'll see how to implement that in Java. Okay? Just say one more thing. So think about this part here has no recursive call. No recursive call to the explanation mark. Because that's a problem we're trying to solve, right? The recursive solution will look like this. So the recursive solution. And to really devise the recursive solution, let's talk about the two phases, right? Number one, base case, okay? So we start with, if I want to calculate n factorial. So there are two cases, base case and recursive case. Base case is kind of the same as before. When n is equal to 0, by definition, it's just 1. Okay? So you can think about this is base case. That means if I know that I only want to calculate the 0 factorial, I don't need to do any computation, just return 1 right away. No computation needed, base case. Okay? Or very simple computation sometimes. What about when n is strictly larger than 0? So if n is strictly larger than 0, okay, so this will be the recursive case. So in the recursive case, I should somehow call the factorial again, but not really on n, because that'll be the same size. I want to do a strictly smaller size. What the maximum will be n minus 1, right? So in this case, it will be, by definition, n, which is the original input, multiply n minus 1 factorial. This solution here is equivalent to this solution, except this is not recursive, but this one here is recursive. Again, because if you look at this one here, factorial. This one here, factorial. Think about right here, this is a recursive call. And when I make a recursive call, I'm trying to really go for n minus 1 as opposed to just n. So for that part, you can see it's a strictly smaller input on the recursive call. It's a strictly smaller input for recursive call. Of course, it's going to be problematic if I simply say, when I want to calculate n factorial, I'm going to say n multiplied by n factorial, for example, without reducing the size. We'll get there a little bit later. Okay, that's more like a common errors. Any questions so far? Yes, Daniel.
Is it always clear that the function to reuse is, in this case it's factorial, is it always clear to know what is the function that we need to reuse?
You mean, are you more talking about, is it always possible for us to know whether we should solve a problem recursively or using a loop? That's your general question. Okay. So using recursion versus using loops, they are basically computationally equally expressive. They're equally powerful. You cannot really say which one is more powerful. But I can say that there's certain problem type it will be easier for you to solve using a loop versus using a recursion and vice versa. So factorial, you can definitely solve it using a loop, maybe back in 1021 or 1022. Right? In that case, you can easily, I wouldn't use a recursion when I want to solve factorial, but I want to solve this one using recursion just to show us how you can use it, right? So I would say at this level here, you would usually be told explicitly about, for this problem here, do I want you to solve it using a loop or I want you to solve it using a recursion? You'll be told. But once you get to maybe 3101, let's say, for example, that's the more advanced level, in which case you have to decide which one might be better for you, right? Mm-hmm. Good. All right, let's now do a little bit tracing, okay, just to get some idea. Okay, let's now take a look at in Java. Okay, so this one here is our recursive definition for the solution for factorial. Right? Again, you can see calling this and calling that. Right? You can see the same call. It's a recursive call, as we said earlier. And to really translate this recursive solution into Java is usually very straightforward. So I would suggest in many occasions, you may just want to sketch some idea about base cases and recursive cases on a piece of paper. And then once you get the idea very straight, you can then turn that into Java or Eclipse. I wouldn't suggest you go for programming right away. Not in the beginner level. I wouldn't suggest. Okay? Let's take a look at the method itself. So we got factorial. Oh, by the way, all the codes I talk about in the class, they are already on the lecture site. You can also download them, import to Eclipse, and play with them. Okay. So it's a accessor, integer, and then factorial taking some integer. Of course, we assume n is larger than or equal to 0, always. Okay. And then we say we got some local variable result. Eventually, we're going to return it. So what should we assign the result to before we return it? If n is equal to 0. So you can think about this part here is the base case. N equals 0 correspond to n equals 0, in which case 1 and 1. Okay? Versus if it is not the case, then we're going to say n minus 1 factorial versus factorial calling on n minus 1. Right? Exactly the same. Okay? So these two, this is more like a mathematical definition. It's like a Java solution. They really represent the same thing conceptually. All right. So what we need to know is how we can trace them. Okay. So there are basically two ways to trace the recursion. The old school way is to really try to go with a stack, which I'll do for once, okay, together with you for you to get an idea. But as you will see, as the example or input size gets more and more complicated, it's not so worth our time to really do just tracing on the stack, because you can easily get lost about what's the big picture. You might just be like a machine executing, pushing and popping, adding or removing to the stack. So there's another way to really trace the recursion, which I will try to focus more as we solve the more complicated problem, which is using a tree-like tracing. Okay, so let me just summarize what I just said. Okay, so when you want to trace recursion, tracing recursions, and one way is using a stack. Okay, so this is very good in understanding how the chain of method call work. However, not as good building intuition about the recursive solution being correct. But I think for the basic example, you have to know how to use a stack. So you may also expect to see some some question in the exam. But I'll give you some exercise to try it out as well. So that one there, you don't have to worry. Okay, that's one way. You can use a stack, or you can use, we call a recursion tree. I'll show you exactly what that looks like. Recursion tree. So this would be exactly good for building some intuition about why your algorithm is actually correct. So this will be the way to go. All right. Okay, so this is actually good for building intuition. Okay, but you should know both. Okay, let's now go back here and let's try to trace a very simple input. But that one there can already give us some idea about the two different methods. Okay, let's say we want to trace about factorial of 3. All right, very simple. Okay, and to do that, I would suggest we start with maybe the higher level, not the stack just yet. We can use a higher level to let us know roughly where we should really go. Okay, So what's going to happen is I'm going to start with the method called factorial 3. Okay? And now for this current input 3 over here, I know that 3 is not a base case. That means I should really, rather than calculating this, let it suspend just for now. Instead, I should calculate this one here instead. By definition, it should be 3 and factorial recursive call 3 minus 1, which will be 2. All right? So rather than calculating this directly, it's going to be 3 multiply factorial of 3 minus 1, which will be 2. So when we do the split right here, you can think about this guy here is being suspended. All right? Now, for this one here, do we have a result right away? Is it a base case? Not quite, because 2 over here is also not 0. So that means we're going to split it further using this. So that one there should be split to 2 times factorial of 1. All right? And at the moment, we got this one suspended, this one suspended. Should we suspend this one as well? We should, because 1 here is also not yet the base case. So we're going to split it into 1 multiply factorial of 0. So now, should we suspend this any further? We shouldn't need to, because 0 here matches exactly a 0, which is going to return 1 eventually, right? So you can think about this one here is going to give us back 1. Once we got this 1 back, we will now be able to calculate 1 times 1, which will be 1. And this will be the result for this one that's being suspended. All right, let me say that again. Once we get this return result, we can continue with the computation, which will be 1 times 1, which will give us 1. Once we get 1 here, this will be the return result also for something that's been suspended here, which is factorial 1. All right? So that will be 1 times 1. So this one here will be also 1. All right? So now when I calculate 2 times 1 here, it will be 2, which will be the result for factorial 2 that has been suspended, right? So that one there is going to be 2. And when I do 3 times 2, it's going to be 6, which will be the result for here, eventually. All right? This is more like a higher level to trace, but when we look at the stack tracing method in just one moment, you'll be very similar. Okay? Any questions so far? Okay. Why don't we take a look at the stack tracing? Okay, we'll do that. And of course, when you do the stack tracing, you got to be very patient and also careful about which method call you are. So I'll try to do that together with you. Okay? So we're going to start with this particular method call here, and then that will be suspended. We're going to make the first recursive call, and then we're going to make a second recursive call, and then we're going to make a final recursive call, which is here. And that final recursive call is going to reach the base case. So the essence about recursion, once you get more and more experience, is you got to make sure at some point your recursive call should really reach a base case. Otherwise, you will never terminate. Okay, we'll see. All right, let's now take a look at this. So what we do is we'll start with this particular one, factorial 3. Okay, so we're going to start with factorial 3. So what we do is we do 2 things. Number 1, we know that factorial calling this method for the first time. And then the n here will be 3. At the same time, we should put this into the stack. It's now being active, right? So now we're going to put factorial 3 in the stack. We'll start with that. Okay, so now we are in the process of executing factorial 3. And then we know that this one here is not going to be satisfied. 3 is not equal to 0. And then we're going to go for this recursive case. That one there, let's write it down, is going to be 3 times, we have the first recursive call right here, right? Let's now do that. It's going to be factorial 3 minus 1, which will be 2. And as soon as we call this first recursive call right here, we're going to suspend this one here. So at the same time, we're going to put factorial 2 onto the stack. Okay? And then, so now for this particular, the first recursive call right here, we're going to call this method the second time. And now n should be 2, right? Second time, okay? And we know that we are not going to go to the base case because 2 equals 0 is false. So we are going to go to the recursive case the second time. That one there is going to be 2 multiply factorial 1. Right? Factorial 1. That one there is going to further suspend this method here. So we're going to put factorial 1 to the stack. Okay? So for now, we just keep growing the stack until we reach the base case. Okay? So now when we try to execute factorial 1, we're going to go for this method the third time. So n will now be just 1. However, 1 equals 0, still false. Not really reaching the base case just yet. So what we'll do is we're going to go for this recursive case the third time. So that's going to boil down into 1 multiplied by factorial 0. Okay, as soon as we do this one here, we're going to put factorial 0 onto the stack. Okay, well, of course, this will turn out to be the last method call we're going to push onto the stack. But let's see. When we now execute factorial here for the fourth time, we know that n equals 0 is going to be true, right? So now we got 0, of course. And result is going to be 1. And then we're going to return the result 1. That'll be the first return. So that would mean we're going to remove this. At the same time, think about conceptually, by removing this, that means we are returning the result just 1 right here. All right? And then what will be the next method to actually resume? According to the stack, factorial 1. Factorial 1 used to be suspended because we were calculating factorial 0. But now that factorial 0 already returned 1, you can think about now, this is now being replaced by just 1. Right? So now if you calculate it, 1 times 1 is going to be 1. So this one here is going to give you the value 1. And the value 1 is also going to be the return value for factorial 1. So return also 1. Okay, let's move on. And then the next method to handle will be factorial 2. Factorial 2 used to be suspended because we were waiting for factorial 1. But now that factorial 1 has returned 1, right? We're going to replace that method call here just by 1. All right? So now when we compute it, 2 times 1 is going to be 2. So the 2 here is going to be the result that's going to be returned. And we're going to return 2 for factorial 2. Okay? One more. And then once we got this one here, you can see factorial 2 can now be replaced by just 2. And the next method to really handle will be factorial 3, which used to be suspended because we were waiting for factorial 2. But now that that one there returned 2, replace that by 2. So 3 times 2 is going to give us 6. That one there is going to give us 6. All right. So once we got 6 over there, it's going to replace it and then return 6. So this will be the final outcome for the return value, which correspond to just this one here. Okay. Any questions about this? This example here is actually rather simple because we are only making one recursive call in the recursive case. You can see here, we're only making one recursive call to factorial using n-1. So the way we kind of see the stack, you just keep pushing and then popping, right, in a sequential manner. So it's pretty straightforward to follow. However, in general, you can expect that you may have to make multiple recursive calls in the same recursive case. That's something we'll see quite a lot. So don't worry, we'll get there. Okay? Any question about this one here? We're good? Anything that's kind of not clear to you? Would you feel confident about doing something like this in the exam? Maybe with some study. okay, with some study and practice, okay? Okay, so I think that it's not exactly halfway. Okay, so what we'll do is we're going to talk about one more example, and then I'll give you some tracing exercise. I'll tell you where the solution is. It's already there. And then we'll move on to strings recursion. All right. Okay, let's take a short break. All right. Yeah, just before we get to Fibonacci, so let's look at two very common errors, but they should be quite easy to spot. Okay, let's say factorial. Let's say this is alternative definition. Do you see any error with it? Anybody? Just point it out. Go ahead. There's no base case, exactly, okay? So obviously, you only got strictly smaller input over here. That's good, and make a recursive call, also good. But the problem with no base cases is you're going to run into infinite recursion. We'll see exactly how to get there, okay? Let's now try to trace, not using a stack, but using the other way. Let's say we start with factorial 3. By definition, n minus 1. So 3 times factorial 2. For that one there, 2 times factorial 1, and then 1 times factorial 0. At this point, we should really stop. However, it wouldn't. There's no such condition there to say you want to, when n needs to go to 0, you're going to stop. No. That one there will still go on. For example, 0 multiply factorial minus 1. And etc. Infinite recursion. Okay? Conceptually, it's called infinite recursion. And in Java, it's called stack overflow exception. Which also makes sense. You can think about your stack will simply just grow with all the method, etc. to infinity, conceptually, right? Stack overflow. Stack overflow is more like a programming concept, but mathematically, it's more like an infinite recursion. You just have no base cases to terminate, okay? All right, so for this one here, no base case. Let's look at another one that has a base case. I do have a base case here. I also have a recursive case. But what's the problem with this one here? Yeah?
No return.
Oh, yeah.
There's no return.
There's no return? What do you mean no return? I do have a return.
Oh, never mind.
Go ahead, please. Yeah, I'll let your fellow student try. Yeah, go ahead. Yeah, exactly, right? Okay, that's another very important principle. It's good that you try to make a recursive call right here, but notice that n and n here, exactly the same. Not supposed to be the case. They should be different, or conceptually should be smaller. All right? So this one here is actually going to do the same thing, really. Okay? So let's say here, if I say factorial 3, okay? First of all, it's not a base case, so I go to recursive case. That one there is going to be 3 multiply factorial 3. And then, when I try to do this one here, similar, 3 is not a base case, and then do this one here, it's still going to be 3 multiply factorial 3, and go on. Infinite recursion will stack overflow. Equally bad, I should say. Okay? So the problem for this is, for the recursive call, the input should be strictly smaller. Okay? Again, it's really worth emphasizing about this pattern here. You want to always remind yourself, whenever you pass an input for recursive call, it has to be strictly smaller. The input to recursive call is not strictly smaller. Okay, you still got infinite recursion or stack overflow, the same. All right. Yeah, common errors. Okay. Yeah, just try to avoid them. Of course, but sometimes if you really forgot about these principles, but if you try to program something recursively, but you see the stack overflow in Eclipse, you would know. It should be something about infinite recursion. Okay. All right, good. It's kind of interesting. Let's say, just put it aside, right? Let's say you're trying to program Eclipse, right? Let's say you have loops and also you have recursion. How do you tell the error you're getting from Eclipse, whether it's telling you have an infinite recursion or infinite loop? It's practical information for us to clarify, right? Anybody? Well, infinite recursion, we already know, is going to be actually stack overflow example. In some way, you can see that from the stack, on the failure. What about infinite loop? Don't tell me you don't have any experience having an infinite loop. I have that a lot. Anybody? Yeah, go ahead.
I haven't experienced any clips for another software.
Yeah, let's say another ID should be consistent. Yeah.
Sometimes it just crashes, like you were saying.
Crashes will be one, but I think that before you crash the IDE, you might just find that somehow you will see your computer CPU spinning, because somehow your loop is just running, somehow without stopping. So you don't even get to see any stack. All right? Let me summarize here. I thought it might be nice to pause and think about infinite loop versus infinite recursion. All right? So let me put it here. Okay? So we got infinite loop versus infinite recursion. Okay? So let's talk about infinite recursion. We know that you actually got stack overflow. Exception. Usually you will see that right away. Okay, that's a very good feedback. On the other hand, if you got infinite loop, let's say you're running test cases. So the test case that somehow goes to the infinite loop is going to hang over there. So your test never terminates. I'm pretty sure some of you actually had that. I kind of look at that during the programming test, or maybe during the office hour. Okay. So that one there, for example, infinite loop. So let's say the test case calling the method with infinite loop will hang indefinitely. Okay, until you kill the process, really, until you really say force to quit. Okay, until you force quitting the IDE. Yep, just watch out for the signal from the IDE. All right. So that's certainly different. Okay. All right, so let's now talk about another recursion example, okay, quickly. Okay. You may have seen this maybe in the first year. If not, okay, I'll just tell you this is something called Fibonacci sequence, which is a sequence of number. So by definition, okay, the first two numbers over here are always 1 and 1, always. So we say the first number is called number 1 element in the sequence. So indices start with 1. All right? And also the second number here will be index 2. Okay? Well, they're pretty much like a base cases actually, right? So these are something we know. Starting from item number 3, you can think about, you can give indices. The index 3, index 4, 5, 6, 7, 8, 9, 10, 11, and so on. So conceptually, the Fibonacci sequence is infinite. Okay? So now, here's a definition. Starting from 3 over here, the number should be equal to the previous 2 terms in the sequence. So 2 is equal to 1 plus 1. Similarly, if I want to calculate Fibonacci sequence element 7, it should be these 2 elements, 5 and 6. 5 plus 8 will be 13. Double check one more. So if I want to calculate the 11th element in the Fibonacci sequence, I should really add up the 9th and the 10th. Add up these 2, and you get 89. All right? Hopefully everybody can see that. All right? Okay. So what will be the recursive definition for that? I'll get there. Okay. You can think about, let me just visualize one of them. Okay. If I got, for example, this one here. If I want to compute F8, right? I know that by definition, it's going to be F6 plus F7. And I know that F6 over here is going to be F4 plus F5. And this one here is going to be F2 plus F3. And this one here, oh, F2 is always 1. Okay, F3 over here is going to be F1 plus F2. Okay, can you see what I'm doing here? Okay, let's now see something very interesting, but we wouldn't dive too much deeper into it. Okay, by definition, F5 over here is going to be basically F3 plus F4. Agree? But you can see that the structure for F3 should be exactly like this. And the structure for F4 should be exactly like this. Agree? So I'm going to do something explicitly over here. Okay? You can think about, so now for F3, I can simply copy this guy here. And then I'm going to put it here. Okay, F3. Okay. Let me just do a little bit better over here. So what I did was I can do F5, which will be F3 plus F4. F4 is going to be this entire thing that we just figured out earlier. So I can put F4 right here. Okay, I'll make it a little bit smaller. Okay, right here. And now, this one here is going to be F6 plus, F4 plus F5. F5 plus F6 over here. But do we have all of them already? We do. Because the F5 over here is going to correspond to this part over here. And the F6 is going to have this part over here. You can just do the copy and paste. Okay? So the point I'm trying to make here is the recursive definition for the Fibonacci sequence there is very clear, just based on the pattern. However, when you want to compute it, it's actually a very, very inefficient way to really compute the sequence. But it's beyond the scope for this course, especially when we talk about complexity of the method. We don't have to go there, all right? But try to really get some intuition about how I draw the tree and how I talk about how they can be reused. Okay, I'll make some annotation quickly, okay? So think about, you can see F4 over here. And also you can see F4 over here again. So this part over here and this part here are exactly identical in terms of the structure. So we're really repeating the same computation for many places intuitively. Not very efficient. Okay? What about recursive definition? Okay? Let's now write it down. Okay? So if I want to compute the element at the nth position, right, in the Fibonacci sequence, I know that n here could be 1, could be 2, in which case I can return right away. So it will be 1 if n equals 1. It will be 1 if n is equal to 2. Base cases, right? So there are 2 base cases for Fibonacci sequence calculation, which is completely fine. Normally, base cases, you don't really have to restrict it to just 1. It could be multiple. It could be 1, can be 2, can be 3, but I would say no more than 3, right? You don't have to go for that many base cases. All right, what about recursive case? Any suggestion? Go ahead, please.
N equals n minus 2 plus n minus 1.
Yeah, I agree with you. So to write it down, it'll be f n minus 1 plus f n minus 2. Basically, the number before and the number even before, right? The previous 2 numbers. If n larger than or equal to 3. Very nice. Thank you. So that'll be recursive case. Okay, awesome. All right, so we have seen so far like a recursion example. I would say they're nice. They're more like a hello world example. Usually people like to introduce recursion, so I thought I might just do it anyway. But I think I'm going to talk about one quick exercise to assign to you, and then we should do a little bit more interesting one, to see how we can do recursion on strings and recursion on array. Maybe on array, maybe on Wednesday, maybe not today. Okay, so exercise for you, which I definitely encourage you to try first of all before you see the solution. I'll show you where the solution is. It's already on the lecture site. So this part here is a Java translation. So there's a recursive solution. That's the solution in Java, right? So you can see here, Fibonacci n minus 1 is here. Fibonacci n minus 2 is right here. And also for base cases, you got 1, 2, and also 1 and 2. Total correspondence. All right. So now the challenge is trying to use the call stack and trace Fibonacci 4. It's much more tedious and complicated than you might think. That's why I want you to really try to do it. All right? So exercise. Trace. Trace using a stack. It'll be a very nice way for you to really revisit about how the stack will work and also how method call will work. Also, you got to be very, very careful when you do this, very concentrate. Okay, I think that is definitely a very good exercise. So once you're done, I'll show you where the solution is. You can simply go back to the lecture site, and then you see that right here. Okay, in the recursion section, you can see right here. Under exercises, you can see tracing Fibonacci 4. All right, so that's exactly the exercise. Okay, give it a try, and then if you want to go over the solution with me, that's also there. Okay. Highly recommended to do this exercise. Okay. Okay, we got about 20 minutes. I would suggest we go over some very important string methods, which you can assume that you can actually use them in the exam. Very simple method, but I need to clarify the usage in some example. And then we can do either 1 or 2 recursion on string. That'll be okay for today. Okay. So we are talking about, let's see which slides. So we have done factorial, common errors, and also we have done the Fibonacci sequence. So the exercise I can ask you to do was Fibonacci number 4. Okay, but there's another one on the slide, which will be Fibonacci 5. Okay, take a look at that as well. That one you don't need to really trace. That'll be too much. That's too. It's not really. It's really unnecessary. I think doing the tracing for Fibonacci 4 should be good enough. But for this one here, just take a look at the slide to see how you can structure the tracing conceptually. All right. All right, and then let's now look at strings. All right. Let's now go over this example code very quickly so you'll see all the methods you will need to program recursion. Just a few library methods I want you to get familiar with. Okay, right here. All right, so let's start with how we can visualize a string. Think about string is simply an array of characters. Okay, so let's say we have S, A, B, C, D. Okay, you can think about S over here. Of course, it's a reference type, so S simply points to the beginning of an array of characters. So here we got 1, 2, 3, 4. So that means we've got 4 elements there as well. So 1, 2, okay. So we got 0, 1, 2, and 3. I believe if you're taking 2031, I think the way they represent strings in C has similar concept, like an array of characters. However, they do have something called null character at the end. We don't do that here, right? You don't need to think about having any extra character, like a null character at the end. Okay, you don't have to. Okay, as simple as just count how many characters you have in the string. The array of character will be that corresponding length. As simple as that. All right. So here we got, let's say, A, B, C, and D, right? So this will be just like a S is pointing to A, B, C, D. Okay, let's clarify that. And the next thing. Of course, you can simply check to see whether the string is empty, which contains no character. That one's easy, right? If the array is empty or if there's no character. S is empty, that means no character. Okay. Let's look at one tricky method, okay, which you may have to use a lot whenever you want to call something recursively on a string, because you want to somehow reduce the size of the input. And one way to do it is by using a substring method. Let me highlight. We got substring over here, substring over here, substring over here, and also substring over here. I even try to use a concatenation as well. Okay, let's understand what substring really means. Okay, so you can also look at the Java API to see how they explain, but I'll just summarize them for you. Okay, so whenever I say S dot substring. I should really pass two arguments, I and j, two integers, I and j. Okay? What this does is it's going to return to me some new string objects. Okay? It's going to return another string. We call it a substring. Potentially it could be smaller, like a shorter. Return a substring by collecting the character in some range of indices. By collecting, or you can say including. That might be a little bit better. By including characters from indices. Now, be careful. You might be thinking it should be from index I to index j. No. All right? It should be from index I to index j minus 1. Indices I to j minus 1. Okay? I think you guys actually learned about like an interval, maybe back in your calculus class, right? So you learned about open interval versus closed interval, right? So here, there are two ways to understand this. You can either understand it as this part for I is closed, so I should be inclusive. And then go all the way to j being exclusive. That's an open interval, okay? So that's one way to think about it, or you can think about it's basically from I to j minus 1, inclusive on both ends. All right, so that's really the definition for this method. You cannot change it. It's a library method, okay? Okay, so let's now look at the example here. Let's look at this one, the last. This one's more like a special case. I'll get there, okay? Let's look at maybe this one here. When I try to say substring 04, you can think about right away, it's as if I'm trying to get all the characters from 0 to 4 minus 1, which will be 3. So basically collecting all the characters 0, 1, 2, 3, entire string. So it's simply ABCD, the original string. Okay? What about 1, 3 over here? It's going to be from 1 here inclusive, but now 3 here should be 3 minus 1, which will be 2. It's going to give me index 1, index 2. So this is a substring, which will be BC. All right? And how about this one here? Any idea? T3. What is it going to return? Well, you might see the answer anyway, but can you kind of picture what's happening there? When I say substring 02 concatenated with substring 24. Daniel?
It's going to return a string from 0 to 3.
You just return the original string, right? Good. So let's think about what's happening here. By definition, just this part here is going to give us the indices 0, 1. So 2 minus 1, right? And this one here is going to give us 2 and 3, 4 minus 1. So overall, we want to concatenate them together. So we got indices 0, 1, and also 2, 3 right here. So you're going to get the original string, which will still be ABCD. Okay? That's why you can see that the T3 here is exactly the same as the original S that you're calling the substring on. Okay? Right? The special case is here. If I got 0, 0, or if I simply just give you the same values for the two arguments, what's going to happen here? Okay? So by definition, again, every time you got any doubts, go back to the basic definition you know. This one here is going to give us 0 and then minus 1. Right? So here you can think about 0 here, minus 1 will give you minus 1. So now the way to understand this one here is, before we think about how many characters should be collected based on this interval. Should be 0, 1, 2, 3, 4 of them. And this one here should be 1 and 2, 2 of them. How about this one here? How many characters should we collect? When we say from 0 to minus 1. None. Okay? Let's do a little bit of math, a little bit, okay? When you think about the size of interval, for example, when I talk about, let's say, if I say 2 and 4, okay, the size. So I basically got 2, 3, and 4. So the size should be 3. Agree? Okay, let's do one more. And then I can give you the rule. Let's say I got 0 all the way to 6. Size? 7. Agree? Because you go from 0, 1, 2, 3, 4, 5, 6. So 6 plus 1, basically 7. All right? So here you got basically 0 to 6. So here is a formula. Whenever you got an interval going from A to B, okay, to really see the size, it will be B minus A plus 1. Okay, so 4 minus 2 plus 1 give you 3. 6 minus 0 plus 1 give you 7. All right, and of course we're assuming that it is important this formula will only work given A should be less than or equal to B. If B is much, much larger, this formula wouldn't work. Okay? So now let's keep that in mind. And now, if you go back here, apply the formula, the size, 0, okay? So it should be B minus A plus 1. So it should be B minus A plus 1, which will give you 0. So by definition, the size here will be 0. So if you try to call the substring on the two values which are the same, it's going to give you empty substring. All right? Some subtlety here you have to know. Okay? Questions? All good? Okay. And then let's now take a look at one more method that you might need. That would be whenever you want to run a loop, for example, you want to get character by character in the string, in that way you can use the character at. Think about that's more like indexing into the array. So character at, so a little bit like a S and then at index I, just like that. But it's a library method you have to call. If I want to go to a particular character in the string as an index, I can use char at. Okay, over here. Right, so in the exam, you can actually use it's empty. You can use the substring. You can also use the character at, or you can also use another method, which I'm going to highlight here. It's called length, which is a method as well. You can see how many characters are there in the string. Right, so these are the methods you can use, but that should be sufficient for any problem I might give to you to solve. Right, questions? Daniel. Sorry, say it again.
In Python.
In Python.
Programming language. Index minus 1 returns the last element.
Oh, interesting. You kind of wrap around, right? Fortunately, not the case for Java. Yeah, it could be confusing in some cases, right? So that is not the case for Java. You don't need to worry. So I think for Java, so you can think about string, it's just like a regular array of characters, in which case you'll be exactly from 0 all the way to length minus 1 for the indices, right? Mm-hmm. All right. Okay, I think we have time just do one recursion problem, just one. Okay. Okay, so now we got all the foundations we need. So let's now solve problems. Okay, at least we do one today. Okay, palindrome. All right. Again, it's a very like a simple one people usually like to talk about when you want to solve recursion on string. Okay, what's a palindrome? A palindrome is basically a word or a string that reads forward and backward the same. Okay, that's a palindrome. So now we want to write a method. It's going to return either true or false. It will be true if the input string is a palindrome. It will return false if the input string is not a palindrome. Okay, true or false. Let's see some example. Is empty string, by this definition, palindrome? If you read empty string forward, backward, just empty string, right? It's a palindrome, by definition. So whenever you want to talk about recursion on string, the typical base case would be string of length 0, length 1, length 2, etc. Some very small length. That's usually the case. Similarly for array as well, which we'll get to on Wednesday. And then, what about just one character string? Palindrome, right? If you read it forward, backward, just A, right? Let's get something a little bit more, not the base case anymore. How about madam? Read forward, backward, right? M-A-D-A-N, you can try, forward, backward, also the same. Another example, for example, race car. You can double check, it's also a palindrome, right? You can figure out other palindrome as well. And then this one here, man, is it a palindrome? It's not, right? Because M-A-N, backward, N-A-M, not the same, right? So it's not a palindrome. So now we want to, of course, you can try to solve this method here iteratively, use writing a loop. I'm pretty sure you know how to do it, right? You can apply what you learned from 1022, you can do it. But now let's try to think about this problem here recursively. It's kind of fun to think about recursively, okay? Okay, so these are the inputs that we just talked about right here. Okay, we got a race car, we got this one, all right? We want to think about this problem recursively. You don't want to look at the whole string. You don't want to, okay? Usually when you want to do recursion, you want to think about if I can just look at maybe something just to begin with, or something ending. These are usually the place you want to look at as a base case, all right? So for example, let's say here, you can see I got R and R. If I read forward, I'm going to see R the first. If I read backwards, I'm going to see R the first. So that's somehow they're symmetric. So now given that R and R are the same, am I guaranteed it's going to be a palindrome? Not necessarily, but at least I should really bother to go further to look at whatever that's the rest, the string. Right? That's kind of like a thinking here, right? So given that first and last character are the same, I know that I may have to look at what's really the middle. And again, when I go to the middle part, which is something strictly smaller, I can also try to look at the first and last character, which will be A and A. If they're the same, I'll try to look at the middle part, which will be CEC, and so on. Let's see another example. Okay? So now for this one here, I try to look at, again, the first and second. You don't try to look at the whole thing. That's not how the recursive thinking is going to work. If I look at the whole thing, A and S. Now they're already different. Do I need to bother to even look at the middle? I don't need to, because I know that for this string here, when I read it forward, it's going to start with A. When I read it backwards, it's going to start with S. They're already different. There's no need to go for the middle part. No need. Okay, let's see one more. So this part here, I don't need to look at that. No need to inspect. And this one here, I need to inspect. And it's because for these two, they are the same. They are the same. But for these two, they are not the same. So I don't need to look at them any further. Okay, how about this one here? Similar. So let's say R and R. That's good. And then I do A and A, which is good. I do C. Okay, this one here. I do R and R. They're the same. And then I do A and A. They're the same. And also I do C and then C. They're the same. Right? But now, if I look at that, this middle part here, EA, AE, they don't read the same. So I don't somehow want to say it's not a palindrome. Okay, so just some intuition here, and then maybe I'll pause here. So think about, based on this kind of observation here, are you able to think about some recursive solution? Hints for you. In order for you to judge whether a big string is actually a palindrome, you may just want to look at the first character that you're going to read forward and the first character you're going to read backward, namely the last character. Compare these two first. If they are the same, in that way, you may want to look at some substring that is strictly shorter and then make a recursive call right there. If these two characters are not the same, you know that you can return false right away. Okay? Think about this intuition here. Okay? And then I think on Wednesday, we're going to finish off the 3 problems over here, and we can talk about recursion on an array. All right, thank you. I'll see you on Wednesday.